Let's pull back the curtain on one of the most fundamental pieces of tech you use every single day, the operating system. To really, truly get it, we're not just going to look at it. We're going to build one, right from the ground up, layer by fascinating layer.
I mean, really think about it. You push a single button and this entire complex world just springs to life on your screen. How does that even happen? Well, we're about to go on that exact journey, from a totally blank screen to a full-fledged desktop. And to make it all click, think of it this way. We're architects. We're about to construct a massive, high-tech smart building, starting with the foundation and going all the way up to the penthouse.
You know, any great building has to start with a solid foundation. And in the world of computers, that means two things: the actual, physical parts, and that first jolt of electricity that brings it all to life. This is where our whole story begins. The second you hit that power button, you kick off this incredibly precise chain of events called the boot sequence. And nope, it's not magic. It's actually a super careful, step-by-step dance. Let's walk through these first few critical steps and pour the concrete for our digital skyscraper. Okay, so level 1. This is the dirt, the concrete, the steel beams. It's the physical stuff you can actually touch: the CPU, the RAM, your hard drive. This is the non-negotiable reality of our building. Without it, we've got absolutely nothing to build on.
Next up, at level 2, we find the BIOS, or its more modern cousin, UEFI. This is basically our building's main circuit breaker. As soon as the power hits, it's the very first piece of software to wake up. Its first job, a quick safety check called a power-on self-test, or POST, just to make sure all the essential parts are there and working before it passes the torch. Once the BIOS gives the green light, it hands things off to level 3, the bootloader. Think of this as our construction site's foreman. And this foreman has one single incredibly important job. They take the master key, find the building manager, that's our OS kernel, out on the storage drive, and then escort them into the main office, basically saying, "Okay, boss, the place is yours, here are the keys."
And with that handoff, we have arrived at the single most important part of our entire building. We're about to meet the brains of the whole operation, the absolute heart and soul of the operating system.
Welcome to level 4, the kernel. This is our building manager. And here's the key. It runs in a special, privileged state called kernel mode. Think of this as having the master key to every single room in the building, plus control over the power and water. From this moment on, absolutely nothing happens without the kernel's direct say-so. So, what's on our building manager's daily checklist? Well, pretty much everything. It decides which programs get to run and when. It manages every last bit of memory. It controls access to every single file. It handles all the communication with the outside world. It's the central nervous system for the entire machine. Now, to keep this whole building from descending into chaos, the kernel enforces one absolutely critical rule. There are two modes. There's kernel mode, where the manager has total power, and then there's user mode, where everyone else, all our apps, has to live. They're basically tenants in their own sandbox offices. If they need something, they can't just go get it. They have to file a request with the manager. This one idea is the bedrock of all modern computer security and stability.
Okay, so our kernel is the boss, but our building is full of all sorts of weird equipment from a dozen different companies. You've got your graphics card, your printer, your network card. How on earth does one manager talk to all of them? Well, that's where our next layers come in. They're the universal translators.
At level 5, we meet the device drivers. Our building manager is a genius, but they only speak one language. They don't speak NVIDIA or Intel or HP, so they hire a team of expert translators. A driver's job is to take a generic command from the kernel, like draw a picture, and translate it into the very specific, unique language that that exact piece of hardware understands.
Right above those translators, at level 6, is something called the hardware abstraction layer, or the HAL. If drivers are translators, you can think of the HAL as a complete set of universal power adapters. It smooths out all the weird differences between various types of hardware, creating a standard set of plugs for the kernel to use. It makes the kernel's job so much easier.
And if you want a perfect real-world example of why this matters so much, just look at this. This is incredible, right? It's the reason the exact same operating system can run on a desktop PC with an Intel chip and a laptop with a totally different ARM chip. The HAL is the magic layer in the middle that handles all those differences so the kernel doesn't have to. It's a game changer. Okay, big moment here. Our building's core infrastructure is officially complete. The The foundation is poured, the manager's in charge, all the internal systems are talking to each other. Now it's time to cross that crucial line from kernel mode into user mode and finally open the doors for business.
This brings us to level 7, system software. This is basically the building's shared utilities. We're talking about the plumbing, the electrical grid, the elevators, all the essential tools and services that every tenant is going to need to function. This way, every single application doesn't have to build its own plumbing from scratch.
And at last, we arrive at level 8. The entire reason we built this skyscraper in the first place, the user applications. These are our tenants. Your web browser, your favorite game, your word processor. They're the businesses renting out the office space. And remember, they're all doing their work inside that safe, restricted user mode sandbox.
And this is why that whole user mode sandbox is a stroke of genius. You've seen this a million times, right? An app freezes or crashes. Well, that's just one tenant in one office having a bad day. Because it's sandboxed, it can't take down the building's main power grid. The kernel just steps in, shuts down that one faulty process, and the rest of your system just keeps humming along. It's the secret to modern stability.
So we've done it. We've built our digital skyscraper, from the bedrock all the way to the penthouse. But you might be wondering, why all these different layers? Why go through all the trouble? What's the genius behind this design?
Well, it all boils down to these 4 brilliant ideas. First, stability. One messy tenant in one office can't burn the whole building down. Second, security. Tenants aren't allowed in the basement to mess with the building's wiring. Third, portability. Thanks to the hail, we can pick up this building and put it on a completely different plot of land. And finally, modularity. We can swap out an old AC unit with a new one, like updating a driver, without having to tear down and rebuild the entire structure.
You know, this layered architecture is the reason our computers are so incredibly reliable. It's been the blueprint for stable, secure computing for decades. It's an absolute marvel of engineering. Which just leaves one huge, exciting question to think about. As our world changes, what's the next great leap in OS design going to look like? What's the blueprint for the next generation of digital buildings?